Okay, so in this problem, I have a traffic light hanging from a beam. Notice that I have a beam, like a fixed beam. So we're going to go back to the table that we talked about in the beginning. And when I have a fixed beam, how do I model it? Well, when I have a fixed beam, I have these pinning forces, but I also have the torque that's exerted by the beam. So basically the force that's preventing the beam from slipping down is a torque that's basically holding it up. So I need an opposing torque at the base of the beam. Okay, so that's what I'm going to do here. Okay, so that's how I model my system. I model it with a horizontal, like a normal force, basically, because it's touching this surface, and then a vertical force because it's not moving up or down, it's pinned. So I need those two forces to pin it at the location, and then I need a torque to prevent it from bending down. Okay, so we're asked to determine the forces and the torque exerted by the screws on the beam. So this is what we're trying to find, all of the forces at the base here. Okay, so this is the statics problem. So because we know that everything is in equilibrium, we know some forces in the x is equal to 0, some forces in the y is equal to 0, and the sum of torques is equal to 0. Okay, so what are some forces in the x? Okay, so let's look at our free body diagram. So I have h, okay, equal to h. And then my sum of forces in the y direction, I have this positive v and then these two negative values here. So let's go ahead and do that. So that's equal to v minus 980 newtons. Oops. 80 newtons minus 490 newtons equals 0. Okay, so I know right away I have my h is equal to 0. Okay, and then my v, I also have a value for that because it's the only variable in that equation. So my v is going to be equal to 1470 newtons. Okay, so I have this value and I have this value. Okay, so I also need to find the torque at the base of that beam. Okay, so I am going to do an equation for the sum of torques, and I'm going to find the torque at that location. So I know that the net torque for the whole system is going to be equal, so I need the beam to have a resistive torque to oppose all the other torque in the system, basically. Okay, so sum of torques equals 0. So first, at the base of the beam, I have an opposing torque, okay, that I'm going to put in. Then I have this negative 980 newtons. So this, I keep making it as 98, 980 newtons. And then the distance it is away. So this is 5 meters. The whole thing is 5 meters. So half is going to be 2.5 meters. So 2.5 meters. And then just to recap what I'm doing here, the torque equation is equal to RF sine of theta. So theta being the distance, the angle between R and F. And R is like a vector, or R is the line between, or R is the R is what the force is acting on, basically, to cause a moment or cause a torque at the pivot point. So R is not only the distance between the force and the pivot point, but also the lever that the force is acting on. I don't know, that was so hard to get out into a sentence. And this is sine of 90 degrees because, as we note, that's the angle. So this is my R for this first guy here, right, 2.5 meters, and my angle theta is 90 degrees, and my force is 980 newtons. Okay, what else? Then I also have another one, so minus, so this is the torque from the bar. So like the weight of the bar causes its own torque. Then I also have the torque from the traffic light. And the torque from the traffic light is 1 meter in, so it's 4 meters total away, right, from the pivot point. Okay, so let's look at, so the force is 490 newtons, the distance is 4 meters, and then the angle is sine of 90 degrees, right? Because this is, again, 90 degrees between the force and the distance, and between the force and the lever. It's like R2. Okay, cool. So we've got everything going on here, and this was the torque of the light, right? So this piece here was like the torque of the light. This piece here was the torque of the bar. So let's rearrange some stuff here. Let's kind of put it all together. Can make this look a little bit nicer here. Okay, torque of the light, torque of the bar. Okay, so all of that is equal to 0. So if we solve for our general torque, right, at the base that's going to need to oppose all these other forces, we're going to end up with 4410, so 4,410 Newton meters. Newton meters being the units for torque. Okay. So yeah. So I just kind of want to zoom in a little bit. So the forces like are kind of exerted by these screws themselves. If you imagine each of these is sort of like a pinning point, there are these upward forces that are exerting this 1470 Newton V component. So this is the V component, right? And then the torque is obtained with the horizontal forces. So these two forces are of the same magnitude because this H goes to 0, right? These two are opposing each other. H goes to 0, they're balanced, but they're a distance apart, right? And so they're actually causing this torque force, right? They're causing this torque that prevents that beam from going down. So this is how that beam is actually generating the torque to prevent that rotation. So hopefully that kind of makes sense to sort of conceptualize like how that beam could have like this sort of like rotating force and what is actually going on there and like how that H could be equal to 0.